This video is a review of the unit circle, sine, cosine, tangent, and the inverse trig functions arcsine, arccosine, and arctangent. Remember, the unit circle is a circle with the equation x squared plus y squared equals 1 squared. So this comes from the generalized formula of a circle, x squared plus y squared equals r squared, except for the fact that our radius here is 1. For any given point on the unit circle, there is an angle theta that kind of determines that point. The x-coordinate of that point is cosine theta, and the y-coordinate of that point is sine of theta, if this is the angle theta. Now, for the generic circle with a radius of r, and centered at the origin, for a point here, determined by an angle phi, x equals r cosine of phi, and y equals r sine of phi. When we draw an angle theta, we always start right here along the positive x-axis. This is referred to as the initial side of our angle. And then, if our angle is theta, here, the other side of our angle will be known as the terminal side. Remember it by thinking that the terminal side is where the angle terminates. It's the end of the angle. Angles that end in the same place, such as 390 degrees and 30 degrees, are referred to as coterminal angles. The smallest angle that a given terminal side makes with the x-axis, so here or here, is known as the reference angle. So, for the red terminal side, this would be the reference angle. The yellow terminal side, this would be the reference angle. This would be the reference angle for the blue, and the green would be the reference angle here. Now, we defined our x here to be cosine theta, and our y to be sine theta. So now we want to think about the function tangent of theta. Now, tangent theta can be thought of as y over x, or as sine theta over cosine theta. Those two are equivalent. Now, if you're observant, you'll notice that y here, this distance, is the rise, and x here is the run. So rise over run, and that means slope. So we can think of tangent theta as being the slope of the terminal side of our angle. This might also be referred to as a grade or a pitch in story problems. So grade and pitch kind of mean the same thing as slope or steepness. Now we can label the coordinates on our unit circle using exact values based on our 30-60-90 triangles and our 45-45-90 triangles. And then we can go on from there and write our values for tangent as well. So I have that off to the side. Notice that tangent of 90 degrees is undefined. So one last thing, since tangent equals sine over cosine in the unit circle, it also equals r sine theta over r cosine theta in a generic circle, in which case the r's simply cancel and we simplify to just sine of theta over cosine theta. And that makes sense because if the tangent is the slope here of the terminal side of our angle, it's not going to matter how big the circle is, it's just going to matter which direction our terminal side is going, or kind of directed towards, and that is just dependent on the angle and not on the radius of our circle. To plot my sine graph, I'm going to use my 4 quadrantal angles, and keep in mind 0 degrees and 360 degrees lie on the same place. They are coterminal on the unit circle. So I'm going to look at 0 and 360 together, so my sine here is 0. At 90 degrees and 270 degrees, my sine is going to be 1 and negative 1. And at 180 degrees, my sine there is going to be 0. So I simply plot those points and then connect them appropriately to draw a sine graph. For the cosine graph, I'm going to do the same thing. I'm just going to refer to my quadrantal angles. So the cosine of 0 is 1, and then the cosine of 90 and 270 is 0. And then I also have that my cosine of 180 is negative 1. So I plot these and simply draw in my cosine graph there. So on my sine graph, or here's my cosine graph and my sine graph, I only drew in the graph from 0 to 360 degrees because these graphs are periodic with a period of 360 degrees. So that means every 360 degrees the graph just repeats itself. So my sine wave here actually goes on forever and ever and ever and ever and ever, just like so. Now, just a reminder, since they have a period of 360 degrees, that means that a shift left or right of 360 degrees is not going to affect the graph. It's just going to be overlapping with itself, and you're not going to be able to see a difference. Now, since our graphs are periodic, and these are wave graphs, they also happen to have an amplitude and a midline. So remember, the amplitude on our graph, or I guess we'll start with the midline. The midline is the average between the highest and lowest point on your graph. So in this case, the average between 1 and negative 1 is 0. So y equals 0 here is the midline of our graph. The same with our sine graph. Our high point is at 1, our low point is at negative 1. The average here, 0. So 0 is the midline of our graph. Now the amplitude is the distance from the midline to the lowest point, or the midline to the highest point. Since the midline is in the middle, it doesn't matter which one we measure. So for the cosine graph, that distance is 1. And then that's also the case here for our sine graph. Our amplitude is 1. Boom, just like that. Now, just like the horizontal shift did not have, or let me start over. The horizontal shift did not have an effect on our graph if it was the same as the period. Otherwise, it does shift the graph and you can see a difference. So it would be just a little bit off. Now, for the amplitude of our graph, that is affected by a horizontal or vertical stretch, or just a vertical stretch. Wow, I'm getting really ahead of myself here. Because that would change how far the top and the bottom are from one another. Now, in order to change the midline, you would need to take the whole graph and shift it either up or down, and then that shift would determine your new midline. And lastly, we get to the inverse trig functions. Now, we use the inverse trig functions when we know the value of a side or the ratio of sides, but not about the angle. So for example, sine of theta equals opposite over hypotenuse, cosine of theta equals adjacent over hypotenuse, and tangent of theta equals opposite over adjacent. So it may be the case on our right triangle here that we want to know the value of this angle, we'll call it theta. We don't know the angle of our theta, but we do know maybe the measure of 2 or all of our sides. So depending on which side we know, that would determine which trig function we would want to use to find our angle. So if we know the hypotenuse and say the adjacent side, then we would use cosine because that requires the adjacent and the hypotenuse. If we knew the opposite side and the adjacent side, then we would need to set up an equation like this to solve for theta because that's the information we have. And so we only want to have one variable. So we plug in the information we have and then we solve for our variable. So the first thing I'm going to do is plug in the value of our sides right over here. Now to solve for theta using sine up here, I'm going to take the inverse sine of both sides and then the 2 here, the sine inverse cancels the sine, so then I'm left with theta equals sine inverse of 4/5. This means that your inputs to an inverse trig function are going to be ratios of sides of your triangles, so they're going to just be length measurements, and then your outputs are going to be your angles. Now, just as sine inverse of 4/5 equals theta, cosine inverse of 3/5 equals theta, and tangent inverse of 4/3 equals theta. So if I'm not sure which one I need to use, I always draw a diagram of my scenario. I determine where my theta is, where my opposite side is, my adjacent, and my hypotenuse. I fill in those values with numbers, so I see what information I do have, what information I don't have, and then I just think Sakatoa. And then I determine which one of these I have the most information to use, and then as long as I've got 2 out of 3 pieces of information, so either the angle and a side or 2 different sides, then I can use that to determine the rest of the information about my triangle. Now remember, if you're looking for the third side of a triangle and you have 2 sides, you don't even need to worry about what's happening with the angles if it's a right triangle, because you can always just use the Pythagorean theorem. There's no need to overcomplicate things.